Volcanoes are the richest source of rock from deep inside the Earth. The most active is in Hawaii. This is the closest we can get to what it's like at the center of the Earth. It's a reminder of the heat and power hidden beneath the surface of our planet. Kilauea volcano has been spewing out lava for thousands of years without a let-up. It single-handedly built the island. Molten rock, called magma, surges up from near the Earth's core and blazes through the crust. The stream, known as a plume, lets inner Earth let off steam. It's like a safety valve.
We believe that the volcanism at Hawaii is ultimately caused by a hot plume rising up beneath it, which occurs because material at the bottom of the mantle is heated up by the core. The core's maybe 2,000 degrees C hotter, and heating it up causes it to become less dense, and then it rises through the mantle. A good analogy is with a lava lamp that you might see in someone's living room.
It's lamps like this that show us what's going on in the Earth's mantle, the layer between the core and the crust. Rock, heated by the core, rises while cooler material sinks from the surface. It's this never-ending process, known as convection, that pushes magma to the surface, where it erupts as lava.
Hawaii is a bit of a special example. It's the most active island volcano that there is. It erupts with extreme frequency, and it's also exceptionally runny, and so the lava flows tend to move very fast. And they have a high proportion of these so-called pahoehoe surfaces, which are these beautiful, smooth, ropey textures that you see.
Lava can build, but it can also destroy. It can seldom be diverted, and it wipes out anything and anyone that gets in its way. Early geologists assumed that such torrents of molten rock flowing out of volcanoes must leave huge voids and caverns behind them. Jules Verne's explorers followed one of these lava tubes as they approached the center of the Earth. But the Earth had one last surprise in store for them. As the professor, Axel, and Hans neared the center, their path was blocked by a rock fall. There was no other route, so they decided to blast their way through. Verne knew very well that molten rock trapped deep in the Earth is under huge pressure. If that pressure is released, it can start a volcano. That's why blasting was a risk. In classic literary tradition, the eruption they triggered blasted our heroes to the surface without as much as a singed eyelash. Eruptions are how the Earth recycles itself. Convection currents in the mantle carry rock to volcanic vents and fire it back to the surface. Volcanologists today can't get inside an active volcano, but they get up close. Tim Elliott plays his part 8,000 miles away.
As geochemists, we tend to come in after the thing's cooled down and then knock bits off.
Predicting eruptions is every volcanologist's aim, but it makes predicting the weather look easy. Lava samples tell us that the Earth's composition is complex, and it changes whenever a large earthquake or eruption occurs. For Tim Elliott, who struggles to keep tabs on this shifting underground world, every sample is a rich source of information. For what will eventually be a highly sophisticated piece of analysis, Tim starts by crushing the lava in a machine Jules Verne might well have designed himself. The first thing is to break the lava into pieces. Then it must be crushed into a fine powder. The next step must be done with great care. The hydrofluoric acid Tim uses to dissolve the powder is equally good at dissolving skin and bone. It eats all the rocky parts away, leaving just the base elements. Those are the parts Tim's interested in. The lava sample is heated and the acid evaporated off overnight.
Once we've got a pure separate of the element that we want, we then take that to the mass spectrometer to analyze its isotope ratio.
Wherever they come from, any two samples of a chemical element will be chemically identical. But we now know that they can differ physically. A mass spectrometer can tell them apart and tell Tim just where in the Earth a sample came from. This one came from very deep indeed.
So that maybe gives us a clue that these things come all the way from the core mantle boundary. But in terms of the ultimate depth of these things, to some extent, I hate to admit it, we rely on the seismologists.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Seismologists can see inside the Earth without going there. Their explosions create shock waves of sound. When the waves hit rock, they bounce back to sensors on the surface. Since different rocks reflect waves at different speeds, seismology lets us map the Earth's subsurface landscapes. Can today's technology take us to the center of the Earth? If so, what would we find there? Seismology lets us see with sound. And there's more to it than creating big bangs, as MIT's Rob Vanderhilst explains.
Seismology is pretty much the only way to get fairly direct probes of the Earth's interior. And there's a lot of development in the seismic theory and observational seismology itself to really give much more refined images.
Seismology is similar to an ultrasound scan that can show an unborn baby in its mother's womb. An image can be created because sound travels through different parts of our body at different speeds. Unlike this scanner, which generates its own sound, seismology can make use of natural sounds that occur every minute or two. The sound of earthquakes, Thankfully, we don't notice most of them, but there are actually 1 million a year. And they're shaking up our ideas about what's going on thousands of miles beneath our feet. Earthquakes are appallingly destructive to human life, but to scientists, they have their uses. The seismic waves are like sonar. By listening as they pass through the Earth, a picture can be built up of a place no one can ever see. First, the waves race through the crust, the skin on the planet's surface. In some places, only 4 miles separates us from the intolerable heat of the magma in the interior of the Earth. The temperature is nearly 3,000 degrees, so intense that the rocks are partially melted. 3,000 miles down in the core itself, the temperature reaches an unimaginable 7,000 degrees. It is the ultimate nuclear reactor, the engine driving the planet.
What we can really image very well is the material that goes down. And in some cases, we can see down to the core mantle boundary. And all that information tells us a little bit about, how density is concentrated in the center of the Earth and how density changes with increasing depth.
Seismologists image rocks. Petrologists make them, mimicking the heat and pressure of the deep Earth.
Now we know where they come from, we know how deep they come from, because the minerals contain elements like calcium and aluminium, and the distribution of these elements between the different minerals depends on pressure. So by simulating the pressure, taking a sample like this and subjecting it to high pressure and seeing how the compositions of the minerals change as we change the pressure, we can go back and work out what depth this particular sample came from.
The anvil on which Bernie forges his man-made minerals is made of tungsten carbide, a material so hard we use it to make drills. He puts a tiny sample of rock in a ceramic tube, a miniature furnace, and then walls it up. The bricks are specially shaped to focus the force he'll apply to them. This way, he aims to reproduce the massive pressures to be found in the Earth.
Over a period of about 4 or 5 hours, we raised the force to around 500 tons, and we then apply a current to the furnace, which is in the middle of that lot, in order to raise the temperature to 1,700 degrees C.
The petrologist awaits the outcome as anxiously as a pizza chef. If the heat and pressure are right, the elements will fuse together into an exact copy of the mineral he's studying. This tells him where it came from. In this case, 440 miles down, where the pressure is 250,000 times higher than at the surface. The advances in science since Verne's time have been breathtaking. And we're still discovering how the Earth was made and how it continues to change. We've come a long way, not in distance, but in knowledge. We've ventured 200,000 miles into space, but as yet, we've only been 7 miles into our own planet. With all the knowledge and technology we have today, surely we can tunnel to the center of the Earth. If we could tunnel to the core, the rewards would be huge. We could shut down our power stations. The energy we tap into would never run out. It would be free and cause no emissions. We could dispose of dangerous waste in the world's hottest incinerator. Huge quantities of minerals are there, just waiting to be brought to the surface. Maybe we could build a high-speed transportation system through the Earth. A global subway. But it's not that easy. This tunnel, linking England and France, took 5 years to construct, and it's only 30 miles long. It's 4,000 miles to the center of the Earth. And would we actually want to go there? It's an adventure that Dan Lathrop would welcome.
Well, it's an interesting idea for an adventure. I guess I'm ready to go if it becomes possible.
Meet the team that's designing the first vehicle capable of penetrating to the center of the Earth. Today's tunneling machines have brains as well as brawn. They drill and support the tunnel as they go and never stop. But what chance has even a smart monster like this of getting to the center of the Earth? Brian Clark has built tunnels all over the world.
If we're tunneling to the center of the Earth, there are different combinations of material, but generally we would start in soft ground tunneling. We would move through into rock, and as we go to extreme depth, the rock would change in character due to the temperature effects. We almost certainly would need to use an arm with a cutter head, tungsten carbide teeth on it to grind and smash the rock.
Today's most advanced mechanical moles can dig 2 feet every hour. At that rate, tunneling 24 hours a day, it would take 1,000 years to reach the center. We'd have to make them work faster, much faster.
And if you think of the tunneling machine as a very large beer can, and it's travelling end on end down through the Earth with cutters up front, the closed face, it means that the cutters cutting away at the soft ground are separated by a wall from the men on the inside, and all of the spoil, all of the earth that's being cut is carried to the surface in pipes.
The amount of rock and spoil coming out of the tunnel is almost unimaginable. We'd need to extract 4 giant truckloads of earth per hour, 100 per day, 36 million truckloads in all. And that's if we tunneled straight down, not on a grade. We'd have to design a new type of vehicle to transport us through the tunnel. Maybe a capsule able to withstand the extremes found deep inside the Earth.
The deeper we go, for every kilometre in depth, we're picking up a 30° centigrade temperature rise, and that is causing us problems. The rock is getting softer, it's getting ductile as a result of the higher temperatures. We're having to resist those temperatures so that people can work within the tunnelling machine, or we would need to produce a remote machine. I think we're now stretching credibility.
But it's not only temperature that will be a problem. There's also massive pressure down there.
I would say it would be incredibly difficult. I think in comparison, the environment as you go deeper into the center of the Earth is much more harsh than what you would find, for the most part, for space travel, with the temperatures and the pressures you'd find.
It's actually a much more hostile environment than going in space or down in the ocean. And in particular, high pressures are such that we wouldn't know how to make a vessel that you could go inside and not get crushed down, you know, really past a few miles. The pressures would start to get too high for any sort of normal technology.
We have ignition sequence start.
We already know a thing or two about building complex vehicles. Could we spin off space technology to help get us to the center of the Earth?
Clearly, one of the biggest issues you're going to have with a trip like that is going to be the extreme temperatures and pressures. Some of the best materials that we have currently for dealing with temperatures like that would be the ceramic tiles on the shuttle, or some kind of carbon-carbon or any type of carbon-based material.
But here's the hitch. While man-made materials like ceramics and carbons withstand heat, they lack strength. Metal is strong, but most steel melts at around 2,500 degrees. The temperature at the Earth's core is probably 14,000. We need new materials to build our capsule, or to shield it.
Sometimes, if time is on your side and you're not going to be exposed to the temperature for very long, simply having a material with enough heat capacity to absorb the heat that's flowing into the system without melting would be sufficient. The best bet that I know of as far as, and even diamond, I think, has a melting temperature of 3,200 Kelvin. So from a material standpoint, I don't know of any materials on their own that would be able to withstand those temperatures.
As well as being the ultimate adornment, diamond is the hardest substance known. We can manufacture diamonds, but could we make one big enough from which to build a capsule?
Well, the diamond certainly would be the strongest material and would allow you to have the highest pressures. It's not entirely clear you, of course, can fabricate an entire vessel out of diamond. That certainly would be an interesting thing and useful in itself if someone could work it out.
For the capsule to survive, it would have to be continuously cooled.
The most difficult thing to overcome is being able to get the heat away from the craft. So the only way to be able to stay in temperatures like that, or to be able to extract the heat, maybe someday with some type of carbon nanotube technology, you could have a very long tether that would follow the craft down to the center, and you could pump some kind of coolant that would go down for thousands of kilometers or however far it had to go, and draw the heat back that way. But without some type of active cooling, I can't see how you would do it.
The biggest problem is the length of time the capsule would be exposed to the extreme heat.
It'd be like trying to build a ship to go in and skirt the sun, you know, it would be that, you know, that sort of nasty high temperatures.
Since the center of the Earth is as hot as the surface of the sun, we couldn't begin to survive there. Space has enormous challenges, but most of it isn't hot. It's a vacuum, so there's no air. But you can take or make your own. And in a vacuum, spacecraft and spacesuits don't have to resist colossal pressure. Exploring space is no picnic, but it's a cakewalk compared to exploring the inner Earth. Every 200 years, this city is devastated by earthquakes. The next one is overdue. Can our Earth capsule save the 12 million people who live here? A tunneling machine using conventional technology would be destroyed by heat and pressure long before it reached the Earth's center. Only 20 miles into its 4,000-mile journey, it would melt. But if one day we could conquer these technical problems, there may be a way we could send a capsule deep into the planet. We'd have to harness the most powerful force on Earth, continental drift. The theory of continental drift, also called plate tectonics, was finally accepted by science in the 1960s, a century after Jules Verne's day. It said that the land masses we're familiar with started out as one supercontinent. This sat on plates that migrated across the globe. But the plates haven't stopped. In another 20 million years, our world will look very different. This is the San Andreas Fault. These two plates are sliding past each other at the same speed your fingernails grow. Most of the time, these plates slide smoothly, but occasionally they get stuck. And this causes earthquakes. Plates don't always slide past each other. In some places, one plate is forced beneath the other. That's what's happening underneath Japan. It looks serene, but beneath the surface, it's a different story. The Pacific Plate and Asia are colliding head-on. Below the picturesque landscape, the Pacific Plate is being driven under Asia, a process called subduction. It makes Japan a hotspot, not just for volcanoes, but for earthquakes as well. Japan's volcanoes look genteel, but don't believe it. It's feared they'll destroy the islands they once created. If we could take our capsule deep below Japan, we'd find that the volcanoes aren't like the ones we saw in Hawaii. At Kilauea, the heat and pressure of the deep earth blast out streams and fountains of molten lava. Under Japan, there's a different driving force beneath volcanoes: subduction. As subduction buckles and breaks the Earth's crust, seawater flows in. Hot rock and cold water are an explosive mixture. Subduction triggers earthquakes too. Tetsuro Orabe is a professor at the University of Tokyo. 8 years ago, a quake killed 6,000 people, including his mother. He now works on earthquake prediction.
Japanese island are located on the western rim of the Eurasian continent, where the plate of Pacific Ocean floor goes down beneath the island arc. So that kind of active setting makes all those natural disasters like a volcanic eruption and earthquake. In 1995, there was a Kobe earthquake which killed about 6,000 people, but it was not predicted, and all the seismological method failed to predict the earthquake.
To predict earthquakes better, we have to know more about their causes. A capsule designed to travel to the center of the Earth could help. If we weren't in a hurry, we could bury it in the Pacific Plate and wait for a few million years. It would end up under Japan, courtesy of continental drift and subduction. The rock we parked the capsule in is solid, but also moving.
And this is what the mantle does. It flows very, very slowly at about a centimetre or so a year. But like glass, if you hit it with a hammer, it breaks.
And that's what causes an earthquake. 150 miles down, one plate tries to move against another. Incredible pressure builds until one slab breaks and slips. Because of its unstable foundations, Japan has one of the most comprehensive networks of earthquake sensors in the world. 1,700 underground sensors listen out for a hint of movement in the crust and mantle. The data is beamed back to a national monitoring center that records every tiny moan and groan. Every quake, however small, is mapped in 3 dimensions. The quest is to find a pattern that will predict future quakes, because Japan is due another big one. It's expected here, Tokyo. Tokyo has a population of over 12 million. Every 200 years, this area is hit by a huge earthquake. The city is built over a busy intersection where 4 of the Earth's plates meet. The subterranean collisions never stop. That's why Japan's so prone to earthquakes, and why it's so hard to see them coming. It's a high-stakes game. Millions could be hurt or killed. To get better data, they will have to drill down into the colliding plates, more than 6 miles.
JADGE stands for Japanese Ultra-Deep Drilling and Geoscientific Experiment. That is to drill about 10-kilometer hole down to the subduction zone.
They've chosen a site, but what about the technology?
The target area of the JADGE project is very active, and probably the temperature could be more than 300 degrees at the depths of 10 kilometers. And then the 300 degrees makes every operation of the drilling very difficult.
And that's the same for our capsule. We'd need more technology for it to survive the intense temperature and pressure. What will the capsule find at the center of the Earth? A mammoth nuclear reactor? On its way to the center of the Earth, our capsule will have to navigate a sea of molten iron. Surging around the inner core, this generates magnetic energy. Just 1% of it escapes from Earth, but that's enough to form a protective shield 37,000 miles out into space. But how is so much energy produced? As Jeremy Bloxham admits, we're still struggling to find out.
Really, the burning question which we all wish to address through our investigations of the Earth's magnetic field is, how is the field generated? What is the mechanism that gives rise to a field which has persisted for at least 2 billion years?
One geophysicist has a radical suggestion. Marvin Herndon speculates that at the center of the Earth, we may find a natural nuclear reactor.
One of the problems that has existed in science is figuring out what is the energy source that drives the Earth's magnetic field.
He doubts that it's just a ball of iron that's been cooling for 4.5 billion years. There's simply so much power. Enough to maintain the magnetic shield, move continents, and make volcanoes and earthquakes. Herndon suspects there's something much more powerful down there.
One of the implications that I suggested early on was the possibility that the changes that we observe in the geomagnetic field may have their origins in changes in the output power of the nuclear reactor.
Could this explain the drastic changes our planet has gone through? Like the extinction of the dinosaurs? Could the melting of the ice caps have been caused by a surge of heat from a nuclear core? Because unlike an iron core, a nuclear one can fluctuate.
A nuclear reactor can shut itself down and start itself up again. Its output can vary, or it can remain very constant.
Herndon's ideas are controversial. Few agree with his theory, and the debate continues. But one thing isn't disputed. The magnetic field is changing, and measurements show it's been doing so for some time.
Based on the results in our current systems that are sort of basketball size, then we have this plan for a much larger system that would be 10-foot in diameter sphere filled with liquid sodium, so about 15 tons of the metal. But it would be driven the same way as the existing experiments, but then at parameters that are much closer to the parameters thought to exist in the interior of the Earth.
The capsule we built to journey to the center of the Earth is under its own power after hitching a ride in the rock. Now, sensors show the going is about to get tough. Miles down, the capsule nears the boundary between the mantle and the outer core. The huge temperature here melts away the remains of the tectonic plate surrounding the capsule. Now, the capsule must be released from its protection and power itself. The capsule drives forward through the liquid outer core. Now, it must cut its way into the solid inner core. It's solid because there's massive pressure here, 4 million times greater than at the surface. And 1 billion amps of electricity surges between the cores. This, at last, is our journey's end, the center of the Earth. The only place on our planet with no gravity. Jules Verne's influence on the world has been immense. He propelled generations of young readers toward careers in science, engineering, and exploration. He inspired the inventors of the helicopter, the submarine, and the radio. There's little doubt that his novels influenced the minds that have changed our world. Little did anyone know, when Jules Verne died at the dawn of the 20th century, that he would have such an effect on the future. His life is summed up in the inscription on his tomb: "Onward to immortality and eternal youth." If Jules Verne was right, maybe one day we will be able to journey to the center of the Earth.